Yes, sir.
Okay, so convolution integral is a very important or powerful tool. It's a mathematical expression actually. In the pressure transient testing, the convolution integral is a mathematical expression of the wellbore pressure in terms of measure flow rate and constant rate pressure behavior of the reservoir as a forward problem. So once that means we have two known parameters. One is wellbore pressure and production value that we are converting it to constant rate pressure behavior of the reservoir and trying to understand the response function from the reservoir. Okay, so the convolution integral mainly deals with simultaneously measured pressure and flow rate at the wellbore of or surface and pressure measurements at different spatial locations in the formation. So what we are trying to record two important parameters. One is flow rate, another is measured pressure. It may be spatial means it may not be a continuous record. We try to gather information of these two parameters and try to convolute it in terms of using mathematical expression to understand the response of the reservoir specifically. Whereas deconvolution is the reverse problem. If the wellbore pressure with the corresponding flow rate is measured, it is then possible to identify the system and to estimate the parameters. That means once we know this, we try to understand the response parameter and take out or estimate the parameters of the reservoir. So that means these are nothing but the operation, some mathematical operation or expression from which we try to understand the particularly the response function. So now to really do a good job in your convolution and deconvolution, our measurement accuracy should be very specific and proper. Okay. So most well testing rate measurements are still made at the surface. You know, we generally measure either at the surface flow line, maybe with the help of a choke, or maybe in the tank. Okay, maybe there is our separator. But the flow rate measurements are slowly entering into the download. Means slowly it is moving to the download so that we get an accurate measurement. It should be pointed out that the accuracy of the surface measurements has improved significantly during the last 10 years compared to the choke regulated or production tank measurement. So it has improved, but still we have certain lacuna or accuracy is not properly done. And we have some problems also that we need to understand. So what surface flow rate measurements have three main drawbacks. What are the drawbacks? Because we lower down our instrument just above the perforation, but we have the fluid seen by the pressure sensor is quite different from the measure at the wellhead of tank. So it's very much obvious because we are lowering down our electron memory gauge below surface at a specific depth, but we are measuring at the surface. So that means whatever the pressure sensor encounters the amount of fluid, it may not be the same where we are measuring. There is a considerable wellbore volume between the pressure sensor and the well head where the flow rate is measured. So there is a volume difference. Okay. So that may lead to an erroneous measurement also. The pressure and rate measurement do not correspond to the same time span. You can understand we are measuring at a specific time below the surface, but the fluid coming to the surface takes some time. So that's why the same time is not recorded in both the cases. At what time we are measuring and what are the amount of flow we are encountering. So this difficulty with surface flow measurements limits the use of accurate measurement of downward pressure as the system response. In any case, if drawdown flow measurements are not possible, then the surface rate should be measured accurately to perform any meaningful interpretation of download transient pressure measurement. So this is very important because what in most of the cases we are trying to get maybe isolated value of pressure and flow rate, and we are trying to convert it into continuous value. Okay, so using our mathematical uh, operations. So for slightly compressible fluid in the wellbore, the surface flow rate can be obtained from the Van Everdingen and first wellbore material balance formula if the surface flow rate is constant or measured. A constant rate schedule is seldom attained for flow test. Okay, so constant rate generally we could not because there may be a lot of problems or maybe you have so many issues related to that. The assumption of slightly compressible fluid in the flow starting is valid only for injection well because we know how much we are doing injection. But when you are producing at a constant rate, because we most of the time we don't could not attain the constant flow rate when you are producing from a either oil well or maybe a gas well. Okay, so for naturally flowing oil wells, the presence of gas as the fluid rises in the tubing causes wellbore fluid compressibility to increase considerably. So as they are compressible in nature, because we are reducing the pressure when we are producing from the sand face to the well head. So that is how you may not maintain the constant rate. So for build up till the sand face flow rate goes to zero asymptotically. So that means what? There is time lag when we are measuring the pressure and the close up, build up test, starting of the build up test. So that means slowly it is going to the sand phase. So that's why the time part is very important as well as the flow rate measurement. So to understand the interpretation and testing aspects of simultaneously measure pressure and wave measurement, it is essential to understand the mathematical nature of convolution with respect to fluid flow in porous media. So this is what the whole system is very much important for understanding our mechanism of the measurement procedures. What type of well we are using for where we are measuring, is it really accurate? So these are what, because whatever value we are using, we may be discussing in the next class for that. What are the precautions or particularity you need to follow when we need to really do our convolution deconvolution analysis. So it's a very simple mathematics. Okay, so what we have an resultant resultant, which are the resultant of the two factors. One is A, one is K, which in terms of time. Okay, so this is actually psi t. That means the basically the star is the convolution product. So the two convolution actually giving us the output result, which is psi t with time. Okay, so the functions psi t is a convolution of the functions f t and k t. These three real valued functions are scalar functions. The convolution kernel is called the unit impulse response or influence function. So we have an influence functions here, which is from the reservoir and is continuous in the domain of 0 to t. So this is what is a time dependent functions, and this is impulse response. The convolution kernel kt in a pressure transient testing is a solution of the pressure diffusion equation at the special position of interest, including wellbore storage and skin. So this is actually the pressure response. That means our diffusivity equation solution. The functions, forcing function ft may be continuous or piecewise continuous and usually time dependent in depending on the reservoir condition. Okay, so that means we have two important parts, which is the pressure solutions of our diffusivity equations, and another is the response function. If you just try to understand our discussion on the compressible zone, so compressible zone, depending on the diffusivity and the storativity and transmissivity, it will respond. So similarly, these two functions are actually getting or giving us an output. So this is actually our output. Okay. So for instance, flow rate measurement at the surface are normally piecewise continuous. Okay. So what actually we are doing, we are measuring, but it is giving us piecewise continuous. If the impulse response or a convolution kernel kt of the system is known, then the response of the system given by equation is output. Okay, so is output result to an input. So the forcing function as known is figure. So this you can see we have given some input parameters. System will respond accordingly, and we are giving it a output result. Okay, so in the well testing terminology, normally the wellbore pressure is output, the production rate is input, and the reservoir model is the convolution kernel. So what we have three important parameters here. One, we are measuring two parameters. One is the output parameter, which is considered to be pressure. Input parameter is the flow rate, and the response functions, or you can say the kernel. Okay, the convolution kernel. Okay, that is actually the system which is giving us as a response. Okay, so the schematic representation of convolution operation as an input and output system. So what we are giving here, the input, which is flow rate. Here we are getting an output, which is actually the impulse response due to the kt. Kt is the system response. So that is how we are trying to use our convolution integral to get the response right. Okay. So here just an example. Here you figure you have a dimensionless time, dimensionless pressure, and dimensionless rate. Okay. So how each and everything is responsible? We have two known parameters. Pressure and rate is known. Okay. So if you see, here is the pressure with time, okay, dimensionless time, and particularly the rate is here, okay. So you can see the rate is here, okay. So, and you have your impulse function is this one, okay. So what is happening? Figure dimensionless variable pressure as a convolutions of the dimensionless impulse response, where KT is substituted GD, okay, dimensionless G, and with time, dimensionless at time given as this. Okay, these are the formulations we have discussed earlier also, these formulations, okay. So what? Which is the impulse response for 1D radial flow? The forcing function Ft substituted QD with time is alpha into Td, the dimensionless flow rate, where Td is the dimensionless time and alpha is the positive constant. We are multiplying with that. So Qd means dimensionless Q is related to some positive values because we are taking the production. So the same figure also present K, GD functions. Okay, this means the kernel, means convolution kernel of the reservoir properties, and particularly the response functions as a functions of dimensionless time. As can be seen from this figure, GD approaches 0. GD approaches 0. This one, when TD approaches infinity. That means this particularly the impulse functions will change when your time is infinity. Dimensionless time. What is dimensionless time? Means when you move away far from your reservoir production area. Okay. So the dimensionless flow rate QD, Porcima subject to dimensionless variable pressure, will increase as QD increases. Moreover, the effect of rapid increase in the QD until TD 0.04. Okay, so here this value. So few seconds. That means this is dimensionless oil bore pressure. Be aware of the dimensionless oil bore pressure. That means we are not getting the real response up to certain time because we have that time the oil bore storage effect is taking place. So we are not getting the impulse function of the reservoir up to a certain time because that time we have your oil bore storage effect mainly. Okay. So now the same graph with a different format. What we have the pressure value, dotted line, pressure value, then rate. This is the rate fluctuating. Okay. And we are getting the impulse like this. Okay. So this is in terms of our normal functions which we have seen earlier also. Okay. Variable pressure changes del P as a convolution of 1D radial line source impulse response in field units. So this is your just like our P at a specific time T. Okay, so this is related to some exponential parameters, and this is the variable radius with T time. Okay, so you can understand how things are changing with time. Okay, okay, so where eta, okay, is related to your K by this, and the rate data T is shown in the figure. Okay. So that means whatever we have discussed so far, this is related to what? Storativity and transmissivity. So as can be seen from this figure, as the previous case approaches 0, T infinity to infinity. That means our response functions will be 0. Impulse functions when our time is high. Okay, time is more. That means there will be no effect of your production. On the other hand, the function Ft forces the oil bore pressure to increase. Ft increases and then both decreases. Okay, so you see initially both increases and then it is decreases. So as above, the rapid oscillation rate at early times is smoothed significantly by a convolution operator. You can see here your impulse function has been smoothened down due to this convolution operator. So sometimes we could say also the convolution integral is a strong smoothing operator. Okay, so similarly, this is a mathematical expression or mathematical operation through which we try to understand how basically the reservoir is responding due to this part. Okay, so this is nothing new. Whatever we discussed so far in everything, now we are using certain mathematical operation to understand more. And even if we don't have the continuous data, if we have a stepwise continuous or the isolated value, that can also be used with the convolution or deconvolution part to understand the whole reservoir in a specific way. Okay, so this is what is the convolution part. Okay, So now the convolution integral given in the equations below has many useful properties with respect to integration and differentiation. That is advantageous in certain respect. When we don't have the continuous recording, when we have certain disparity in the flow rate or maybe the fluctuation of flow rate, at that time we could use, but the data should be properly chosen. That we will discuss in the subsequent class. Okay. So basically the convolution kernel is fundamentally a pressure diffusion kernel and continuously differentiable. It is a solutions of pressure diffusion equation. The forcing function flow rate F is a continuous or piecewise continuous function. Okay, for the convolution integral of the pressure diffusion. So this is what is the advantage is, even if you don't have the continuous recording of your parameters, if you have a stepwise continuous, or if you have an isolated value, you can use that for your convolution integral to get certain parameters of your reservoir. Okay, so this is what is the convolution. Now, what I told you, this is the forward model. Now, what is deconvolution? Deconvolution is the reverse of that. That means we are using this measure flow rate and pressure to get the response, and from that response we try to get the parameters measure or estimate the parameter. So deconvolution techniques have been used increasingly for pressure transient test interpretation. Deconvolution is a mathematical tool that extracts the drawdown type curve from the rate and pressure history. So whatever data you have, either build up or drawdown, we try to convert it into rate and pressure, constant rate and pressure history, right from the beginning to the end of the production. Okay, so deconvolution enables us to reconstruct, compute an equivalent or extrapolated constant rate drawdown response for all production and certain periods combined. This is the advantage. That means even if you don't have continuous data, if you have a sporadic data, so that is the advantage. Even in your certain time also you can convert into the constant rate drawdown response. Okay, so that is the advantage. So although not strictly speaking, the deconvolution constant rate drawdown response can be thought of an extrapolated response. So essentially the deconvolution process consists of the following. Okay, generate a type curve as an initial guess. So what we are trying to have an initial guess, superpose this type curve with the historical rate data to calculate synthetic pressure. So what you could understand, we are trying to superimpose the two parts, recorded pressure and our synthetic pressure, and calculate the error between the calculated pressure and the measured pressure. So what, this is a synthetically calculated pressure and we have measured certain pressure. So now what, if there is a disparity between these two parameters, you can easily try to see why this disparity, then what to take care during our calculations or estimation. Generate a new type curve and repeat the process until the error between calculated and the measured pressure is minimized. So what that means, by comparing or superposing the synthetic pressure and the measured pressure, we are trying to evaluate the response of your reservoir so that I may reach closer to the reality of the reservoir situation. So that is what is advantage in case of deconvolution. So the deconvoluted type curve can then be analyzed using conventional diagnostic analysis technique to determine various reservoir characteristics such as permeability. So what we discussed about different conventional way of analyzing different parameters of the reservoir, semi-log, log-log, diagnostic plot, and then we could analyze. Okay. So here I will discuss certain one thing of your, particularly the fracture reservoir at the end. Okay. Deconvolution provides an alternative to conventional diagnostic analysis and can show additional flow reserve information that would not normally be seen within a specified time frame of the build-up test. Okay, so what is there? If you, because we are extrapolating with the rate, with the constant rate drawdown pressure response. Okay, so sometimes you may test up to a certain temperature, but that can, in case of deconvolution, you could go up to a longer time for understanding particularly your specific type. Or okay, so please note that deconvolution is a purely mathematical process and should be used with caution. So you could understand very simple part, whatever major data you have, we are trying to estimate or calculate in terms of specific way. Okay, so it's an operation, mathematical operation, nothing else. So that's why whatever we are doing, that should be very cautiously treat or very carefully treat, and to take the data very carefully. Okay, the following guidelines show the ideal conditions for deconvolution data obtain the best possible result. Data does not contain a lot of noise. Okay, so data is free from outliers in both rate and pressure. So that's why I told carefully recorded data should be very important. Where you are recording, what are the possible uh, 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 errors you may encounter during your data recording. Rate history is reliable. You should go for a reliable data check. Build up type curves used for deconvolution rate consistent with each other. Wellbore and reservoir property do not change significantly with time. So that means you need to understand your reservoir system right, and then you can see, okay, whenever I have my synthetic pressure and I have a major pressure, so should I change uh, abruptly to just see whatever happening in any case? Okay, so this is what is happening in many cases, and I should be careful. Okay, so now a good estimate of initial pressure is available. So you know initial pressure, knowing the initial pressure is everywhere is very much important, because PI is very important in case of reservoir performance analysis and understanding many of the parameters right. Okay, so that's why you should be very careful what are the errors you are initially introducing into your calculations. Once your initial data are very clear and you should be very confident about the data, then you can go for your mathematical, using your mathematical expression or the convolution deconvolution for doing better analysis. Okay. So to obtain the constant deconvolution behavior or constant pressure and its derivative is very important for system identification and pressure transient formations in the oil testing. So what we are always discussing, how and why the pressure response. We are trying to discuss, or we discussed about the compressible zone, where the compressible zone is moving away. So that means the pressure is out